Hi, everybody. Welcome back to Consciousness and Awareness, Part 2. So, we've talked about basic and moral emotions, and now we need to talk about some other stuff about emotions, specifically how emotions work. And we're going to start with Schachter and Singer's two-factor theory of emotion. There are lots of different theories about how emotions work. And what's really interesting about these is the incorporation of how the body works, how emotions and your physical body interact with each other. And probably the more famous, at least in recent history, is Schachter and Singer's two-factor theory of emotion. So here's what I want you to do. I want you to imagine that you are a caveman, right? So the factors in two-factor theory of emotion is number one, your body experiences a form of arousal. Now, I know you're thinking. You're thinking arousal, sexual arousal. Well, sexual arousal that is arousal, but it's not the only form of arousal. When we say arousal in psychology, we're talking about any kind of arousal. I mean, just your heart beating fast is enough to be arousal. So ideas of your heart beating fast, your eyes dilating, you know what I'm talking about, arousal. It doesn't need to be sexual. It just needs to be arousal. So the first thing that happens is your heart starts beating faster. Then you look at yourself and you're like, why is my heart beating faster? Okay, two factors. One, physical arousal. Two, cognitive interpretation of your physical arousal. That's it, right? So my heart's beating fast. That's part one. Why is my heart beating fast? That's part two. Here's how this goes. You're a caveman. Your heart starts beating fast. You say, why is my heart beating fast? You look around for a reason why your heart's beating fast. Oh, look, there is a dinosaur chasing me. If there's a dinosaur chasing you, then you're like, oh, I know why my heart's beating fast. I must be experiencing fear. However, if you go through the same steps, your heart's beating fast, you look around, why is my heart beating fast? But instead of seeing a dinosaur, you see Wilma, even though your heart is beating fast exactly the same way, now you're in love. You see the difference here? The arousal is the same, right? The actual experience of physiological arousal is the same. The difference is how you interpret it. What this is saying is that your body reacts and then you put a cognitive interpretation on it. So, according to Schachter and Singer's emotions, there are two stages. The first stage is experiencing a change in arousal. That's the first stage, and then you interpret that change in arousal. So, your body responds, then your brain interprets it and responds. Now, if and this is kind of a big if there actually is a dinosaur there and your heart beats fast and you're like, hey, why is my heart beating fast? Oh, dinosaur, I must be afraid. Then you'd be correct, right? Now, by the way, you're not like sitting there and scrutinizing. You're not thinking, oh, why is my heart beating? This happens pretty rapidly, automatic. It's not a like cognitive thing that you're doing. It happens automatically. But you want to figure out why your body is responding the way it is. Now, sometimes that's because there really is a dinosaur chasing you and you're actually afraid. But sometimes your body is reacting and there's no real good reason why. And you look around in your surroundings and you're like, gosh, I don't know the reason why. I'm going to pin it on. And you choose something in your environment to pin it on. Attribution means to find the cause of, to attribute the cause of something. According to Schachter and Singer's two-factor theory of arousal, of emotion, sometimes we experience misattribution of arousal. That means that instead of finding the real reason, like a dinosaur chasing you, our hearts are beating fast, we have experienced this arousal, and we look around for a reason, and we choose a reason that may not be accurate. So, why is my heart beating fast? Oh, I don't know. Oh, look, there's somebody there. I must be in love with them. Not that that person was causing your heart to beat fast. You just decided that must be the source. It's a misattribution of arousal. So what this is saying is that sometimes we may experience very different emotions, even though the actual arousal is the same for both. And sometimes arousal may come from outside things, and we decide that it's based off of an emotional response. Let's talk about an example. Cantor, Zillman, and Bryant in 1975 did a study. Okay, now here's how this goes. There's only one independent variable in here, and the independent variable is the amount of rest. So there were 3 groups, and each of these groups ran for 1 minute apiece. Now, I got to warn you, it turns out that in misattribution of arousal, attraction is pretty easy to misattribute, and specifically in heterosexual men. So you're going to hear us talk a lot about heterosexual men misattributing their arousal. So letting you know, that's what we're going to be talking about. So here's what we got. We got a bunch of heterosexual men, right? All of them run on a treadmill for 1 minute. Then they're randomly assigned to either rest for 1 minute, 5 minutes, or 9 minutes. Notice how I said that they rest for 1 minute, 5 minutes, or 9 minutes. Then, after that rest, they watch a sex scene, okay? Now, the dependent variable is how much did you enjoy the sex scene? So, based off of this idea of misattribution of arousal, what I want you to determine is who liked the movie, the sex scene, the most? Which group liked it the most? The group that rested for 5 minutes liked it the most. Some of you are like, wait a minute, that doesn't make sense. Didn't you just tell me I'm supposed to misattribute the arousal? Yeah, you're right. I told you you're supposed to misattribute the arousal. So here's how this went, okay? The men they ran for 1 minute. Everybody ran for 1 minute. They either rested for 1 minute, 5 minutes, or 9 minutes. Then they watched the same sex scene. Everybody saw the same sex scene. And it turned out that the people who ran for 1 minute and then rested for 1 minute did not attribute the arousal to the sex scene. They're like, hey, my heart's beating fast. Why is my heart beating fast? Oh yeah, it's because I just ran on that treadmill for a minute. That's why. It's not a misattribution of arousal if you correctly attribute the arousal to the right source. That second group of 5 minutes, they ran for 1 minute, then they rested for 5 minutes, then they watched the sex scene, and they're like, hey, my heart's beating fast. Why is my heart beating fast? Well, it's been a while since I ran on that treadmill. I must have really liked that sex scene. The 9-minute group, they ran for 1 minute, they rested for 9 minutes, and then they're like, why is my heart beating fast? But their heart wasn't beating extra fast because of the running. They had rested for enough time that their heart was not beating fast because of the running. And so any arousal that they did have was only from the sex scene, not from the treadmill. The only one who experienced misattribution of arousal was the 5-minute resting group. The 1 minute resting group experienced arousal, but they attributed it correctly to the running. 5-minute group, they misattributed it to the sex scene. The 9-minute group, they didn't have extra arousal, so they didn't attribute it to anything. So, if this is the case, then how would you create a sly spike in arousal, say in class? Say there's someone you're like, hey, I'd like to get them to know me better, and I want them to think that I'm attractive, so I'm going to create misattribution of arousal. How would you do it in class? Okay, now, as you're thinking about this, you've got to figure out, how do I create how do I make their heart beat fast, but how do I make sure that they accidentally attribute it to me instead of somebody else? So I don't know why that went that way. So let's think about how you would do this. If you just go up to them and, sneak up behind them and go, boo, now do you love me? That's not going to work, because when you scare them, they know that you did that and they just attribute it to you being a weirdo, right? That wouldn't help you at all. You want them to misattribute their arousal. So here's what you do. You make sure your instructor is giving a pop quiz. And then they're like, pop quiz. And they're like, oh no, pop quiz. That makes your heart beat fast. And then about 5 minutes later, you're like, hey, how's it going? And they're like, oh, my heart's beating fast. Why is my heart beating fast? Oh, it must be because I'm in love with you. When in reality, it's because the instructor gave the pop quiz. That's one way that you could do it. Now, whether that's ethical is a totally different question. I am not saying that you should do this by any means. I'm just saying that hypothetically, that's how it theoretically could be done. All right, the next step in this. It turns out that arousal, this misattribution of arousal thing, it's not some sort of like love potion that just makes people fall in love with you. That's not how it goes. So we're going to talk about the White et al. Study from 1981, which is also about misattribution of arousal, but it's going to be a little bit different, and it's going to show you some interesting results. So in this particular case, we're looking at how it turns out that arousal actually is probably polarizing what you would normally feel. Polarize means to make more extreme, right? So this is how it went. First, again, heterosexual men are being used in this particular study. Those are the participants. Half of them run for 15 seconds, half of them run for 2 minutes. Okay? Then they are either shown an attractive photo or an unattractive photo. They're shown a picture of a woman who has been pre-rated as either attractive or unattractive. And then they rate how attractive they find the woman in the photo. So if you look at this particular graph, you will see that these are the ratings that the men gave of the different women. So the bluish, right there, whoop, go back, there it is. The bluish color, this is attractive. Notice how it's blue here, right? These are people who are shown the attractive photo. High means high arousal, okay? Meaning they ran for 2 minutes. The men who ran for 2 minutes and saw the attractive woman rated her as more attractive than the men who saw the attractive woman but only ran for 15 seconds, okay? However, look at this. The men who ran for 2 minutes and saw an unattractive woman found her significantly less attractive than the men who ran for 15 seconds. The people who were in the high arousal condition were here in the high arousal condition. These are the ones who had higher amounts of arousal. And it looks like the arousal polarized. The attractive woman became more attractive. The unattractive woman became less attractive. It's not like some sort of love potion that just makes you fall in love with somebody. It seems like it's going to exaggerate how you're naturally going to react. So if you're actually going to use misattribution of arousal, I'm not saying you should, but if you ever did, better make sure that they find you at least neutral to begin with. Otherwise, it could backfire on you. All right, let's talk about something else. You feel stressed? Well, you've told me that you feel at least somewhat stressed. I'm sorry. I hope that everything is okay and that you can deal with it. You've indicated that you're neutral. You're not stressed or not stressed. Well, all right. I hope that you don't get to be stressed and can stay neutral. You've disagreed with feeling stress. Well, good. I'm glad. I'm glad that you don't feel stressed in your life. I hope that you can still feel engaged in things even though you're not feeling stressed. And I'm glad that you're not feeling any negative emotion of stress. So stress is an interesting concept. Let's ask you one other question before we get into this. How do we feel stressed? What is going on when we feel stress? So during stress, things are released in your body. And I want you to tell me which one of these gets released in your body when you feel stressed. Specifically, what is the thing that gets released that suppresses your digestive and reproductive systems? The answer is cortisol. Cortisol suppresses your digestive and reproductive system. So here's what's going on when you're stressed. You should think about stress kind of like, remember the caveman was running away from the dinosaur? Well, that's kind of the same thing that's going on. Your stress reaction is meant to give you the energy that you need to take care of problems. Think like fight or flight kind of problems. So, if some dinosaurs run after you, going to eat you, then you better run away. Now, I know Dinosaurs and humans, not on Earth at the same time. Fine, fine, fine. What? It doesn't matter, right? So the response is still the same, right? Your stress response is saying, hey, let's take the resources away from things that don't matter, make sure that we have enough resources to run away and get it done. So this is really important. Cortisol, for example, suppresses your digestive and reproductive system because you don't really need to digest or reproduce while you're running away from the dinosaur. Adrenaline gives you extra boost of energy. Cortisol, by the way, also makes glucose more available in your bloodstream so that you can use it. But these are meant for you to get away. Now, the problem with stress is that sometimes we feel it in a prolonged period of time. It's like your body's trying to run away from the dinosaur for like days or weeks. That's not good for you, because it turns out for people to be healthy, they need to do things like digest food properly, right? And so if instead of just this short periods of time of you feeling stressed so you can get through, an obstacle of something that's imminent in your life, instead, if you're feeling stressed in a long period of time, it's kind of like your body is trying to fight or flight for days, weeks, months. And that is not particularly healthy. That is why people try to avoid or lessen stress, because it's the prolonged amount of stress that tends to be a problem. All right, which of these is primarily an inhibitory neurotransmitter? If you remember, we talked about this in the past. It's GABA. GABA is primarily an inhibitory neurotransmitter. What we're going to do now is we're going to move away from emotions, and now we're going to start talking about drugs and how drugs work in the body. So let's start by looking through drugs in the synapse and how they work. Now, in order for you to understand this, you got to remember how drugs worked before, right? How the synapse works, how the synapse works in general. When we look at these neurotransmitters, remember that glutamate, and I'll make glutamate just for now, this is just for us. I'm going to make glutamate be a square, okay? Let's see, did it work? Yep. I'll make GABA be a triangle. I'll make serotonin be a circle, and we'll make dopamine be a diamond. What we're going to do is we're going to talk about how drugs work in the synapse. Now, this is a review from stuff that we've already covered. So I'm drawing right here. This is going to be a terminal button in a presynaptic neuron, okay? And then this is going to be the dendrite of a postsynaptic neuron. If you remember, we've got these little water balloony things in the presynaptic neuron. These are called vesicles, and inside of these we have neurotransmitters. So let's say that there's glutamate in this one. Remember, these neurotransmitters are like a key, and there are keyholes on the other side. So let's say that this is a receptor site for glutamate that's on the postsynaptic dendrite. When the action potential comes to the terminal button, it says, all right, vesicles, go to the edge and release your neurotransmitters. So the neurotransmitter glutamate gets released and binds to this receptor site. That opens up a door, an ion channel, and glutamate particularly is excitatory. That means that it's going to let in positively charged ions, which is going to build up the electrical charge in the postsynaptic neuron until it hits the threshold, sends an action potential in the next cell. All right? Now, that's glutamate. Glutamate's excitatory. That's what it does. But different keys open different doors. Neurotransmitters are like a key. And so different keys are going to open different doors. Remember, though, after you're done opening a door, you don't keep the key in your pocket. It goes back into the pocket. You don't keep it in the keyhole. It goes back in the pocket. So the process of reuptake is when the neurotransmitter goes back into the vesicle it came from. Well, glutamate is excitatory, but GABA is inhibitory. So instead of letting the positively charged ions in, if this was GABA, GABA would let in negatively charged ions. That would make it less likely that the next synapse, the next neuron would fire, reach an action potential. Serotonin and dopamine, a little more complicated. Let's not worry about them being excitatory or inhibitory. Serotonin is involved in sensations, the ideas of experience of sensation. And dopamine is involved with feelings of pleasure. Now, in reality, all of these do, more complicated stuff. But for us, if you remember that glutamate is excitatory, it's going to let in the positively charged ions, and GABA is inhibitory. It's going to let in negatively charged ions. Serotonin is involved with sensation, and dopamine is involved with pleasure. It's going to help us understand how drugs work in the synapse. So let's talk about cocaine. We're going to talk about cocaine, alcohol, LSD, cannabinoids, and opioids, and how they work in the synapse. So let's start with cocaine. Remember, dopamine is involved with pleasure sensations. So here's a presynaptic neuron. Here is a postsynaptic neuron. Inside of the presynaptic neuron, we are going to have some vesicles, and in those vesicles, we are going to have dopamine. That was our little dopamines. Remember, they were going to be diamond-shaped. That means that we've got some diamond-shaped receptors over here. That's going to be a diamond-shaped receptor on the postsynaptic neuron. When the diamond-shaped, when dopamine is received by the postsynaptic neuron, it is going to result in a pleasure sensation of some form. Okay? So action potential comes down. It says, hey, release the dopamine. Dopamine gets released and then binds right over here, right there. Okay? When cocaine comes in, here's what cocaine does. Cocaine comes in and it blocks the reuptake of dopamine. It stops dopamine from getting back into the vesicle. The cocaine comes in and blocks that. And if the dopamine doesn't have anywhere else to go, it can't go back in the vesicle, then it just goes back and binds again and again and again and creates a pleasure sensation. All right? That's how cocaine works. It blocks the reuptake of dopamine. And when it does that, the dopamine just binds over and over again. All right? Remember, neurotransmitter like dopamine is like a key. If I can't put my key back in my pocket, then I'm going to keep opening the door, opening the door, opening the door. That's what happens. Okay. This is different, though, when we're talking about something like alcohol. Now, alcohol is a depressant, right? Alcohol is a depressant, meaning we're going to have less action potentials happening, less firing. There's two different ways that alcohol works. Two different ways that alcohol works. Alcohol works with GABA, and alcohol works with glutamate. So GABA, remember GABA is going to be our little triangle. That's an inhibitory neurotransmitter. So when GABA is released into the synaptic cleft, it binds right here. Okay, it binds, and then that's going to let in negatively charged ions into this cell. It's going to make this cell less likely to fire. Well, alcohol comes in there and it works kind of like a doorstop, right? So remember, the neurotransmitter is like a key, the receptor side is like the keyhole, and it opens up different doors. Well, this one's opening up a negatively charged ion door. Well, alcohol comes in here and it keeps that door open longer, right? It just says, oh, we're going to be like a doorstop. We're going to keep that door, that ion channel, open longer than it normally would be. And when it does that, that lets in more negatively charged ions into the next cell. So alcohol enhances GABA, meaning it keeps those negative ion channels open longer so that more negatively charged ions get into the next cell. Alcohol also does something with glutamate. Now remember, glutamate is excitatory. That means that alcohol wants to hurt it. Alcohol wants to stop the glutamate. And so in this neuron, we've got the glutamate, which is kind of like a square, right? And here is a receptor for glutamate. So the glutamate gets released, alcohol comes in, and it blocks the receptor site. It's like putting some duct tape over a keyhole, so you can't put the key in there. If glutamate can't bind over here, then these positively charged ions that are just hanging out, they're just going to hang out and nothing they can do. They can't go in, they can't excite the next cell, and if they can't excite the next cell, then there's no action potential that's going to happen. Okay. LSD. LSD is one of the easiest ones to understand. Turns out that you have some serotonin receptors. I'm going to try to erase this stuff. Hang on a second while this erases. So it turns out that serotonin has some receptors, and LSD just straight mimics it, right? It goes in there and it takes the place of serotonin. Let me see if I can show you what I mean. So we've got a presynaptic cell. Whoop, that's not what I wanted, sorry. Let's see if I can get that to erase. So here's a presynaptic cell, and here is the postsynaptic cell. Here's a receptor site for serotonin. LSD just comes in here and takes the place of the serotonin. That's it. That's it. Doesn't need an action potential from the presynaptic neuron. It just is it's a false key for the keyhole, right? That's all. That's all it is. Okay, that is why, by the way, LSD can create things like hallucinations, because it just mimics those serotonin, which is involved in sensation and perception in your brain. Okay, perception in your brain specifically. All right, then let's erase this and talk about cannabinoids. Now you should know this. Cannabinoids and opioids work essentially the same way in the neuron. I'm not saying that cannabinoids and opioids are the same thing, but on a synaptic level, they work in a very similar way, just with different receptors. So for this one, we're going to need to draw 3 different neurons. So here is a terminal button for neuron number 1. Let's see if that's going to draw for us. Here is a dendrite for neuron number 2. Here's the soma. Here is the axon, and then the terminal button for that. Now I know that's not exactly how it looks, but that's what we're going to do. And then here is the dendrite for number 3. So this is cell number 1, cell number 2, and cell number 3. Okay? Here in cell number 1, in this vesicle, we have GABA. The vesicles of cell number 1 have GABA. But the vesicles in cell number 2, they have dopamine. Okay, now if you remember, GABA is inhibitory. It wants to stop. It's going to create, negatively charged ions to go in. So here's some negatively charged ions hanging out. Whereas dopamine is involved with the with feelings of pleasure. Okay. So in your body right now, I'm assuming you don't have any cocaine or heroin going on in your system. Okay. Assuming that you don't have any cannabinoids or opioids in your system right now. What's going on in your system is there are action potentials that are coming down here, okay? And we've got these receptors over here, and the GABA is binding, and that's opening up the doors, the ion channels that are letting in the negatively charged ions, okay? When that is happening naturally, which is what's happening in your body right now, then the dopamine over here doesn't get released. The dopamine in cell number 2 doesn't get released because negatively charged ions mean you're less likely to release the neurotransmitters in the vesicle. Okay, so right now your body is saying, don't release the dopamine, don't release the dopamine, don't release the dopamine. That's naturally what's going on in your body right now. So let's start with cannabinoids. Let's try to erase this. Come on. Oh, great. Thanks. Let me just erase these and make that dendrite come back. Okay, fine. What a cannabinoid does is a cannabinoid has its own little receptor, and its receptor is on the first neuron. Cannabinoids have one receptor. Opioids have a separate receptor. And what happens is your body naturally creates certain chemicals which stop the GABA from being released. So even the action potential is coming down. If you've got something like anandamide in your system, it says don't let the GABA go, right? Well, what happens is THC comes in here in cannabinoids, and it binds where the anandamide normally would. It binds right here. And what that does is it says, don't send out your GABA. Don't send out your GABA. Okay, so THC for cannabinoids binds right there, and even if an action potential comes, it says, don't send out the GABA. Well, if GABA is not sent out of cell number 1, then cell number 2 is naturally going to release more dopamine, and it's going to bind to cell number 3, and that's going to result in pleasure sensations. So, cannabinoids and opioids both have, they're separate, but both have receptors on the first cell, and they stop the GABA. They say, don't release the GABA, don't release the GABA, don't release the GABA. And when they don't release the GABA, then your body naturally releases the dopamine, and the dopamine results in pleasure sensations. Okay, so to review then, which of these do not primarily affect GABA? All right, so cocaine does not affect GABA, it just blocks the reuptake of dopamine. Alcohol does affect GABA. Remember, it enhances GABA. So cocaine affects GABA. Cocaine does not affect GABA. Alcohol does affect GABA. LSD doesn't have anything to do with GABA. It just mimics the serotonin. But opioids and cannabinoids, those affect GABA. They say stop the GABA from being released. So alcohol affects GABA and glutamate. Cannabinoids and opioids, they affect GABA as well. They say stop releasing the GABA. Cocaine and LSD, they're not involved with GABA at all. All right, everybody. Thank you.